I plan to cover under analog circuits and university titled that subject as electronic circuit analysis. And university asked me, sir, please share PPTs at day wise. So till now I have completed 5 days coaching. So I have shared PPTs day wise, and perhaps they have uploaded and they have shared the link with you. From there you download. My suggestion is you need to understand the derivations, but you are not expected to reproduce in the examinations. Okay? I mean, get examination. What is more important is remembering the main formulae and doing a lot of practice. That's what I have been telling, that you should remember. Better you summarize all the formulae at one place and do a lot of gate questions from previous gate papers. That practice makes you perfect, and perhaps you can manage very well the examination within the given stipulated time. You can answer the paper. So please focus on summarizing all the formulae at one place. Do a lot of practice, okay, to save time, to manage your time during gate exam. Now we discuss about questions from previous gate question papers, solutions, and one of the questions is, it is a question is this: a transistor circuit is given below. G0 breakdown voltage is 5.3. This is a G0 diode connected from base to earth. It has breakdown voltage of 5.3 and 0.5 milliampere current that is flowing into G0. Take base to emitter voltage, base to emitter 0.6. The value of current gain beta is asked. So I will take this point as V dash. Okay, then I will say this current is IB, this current is I0. So I0 minus IB gives 0.5 milliamperes, and what is asked is the current gain. This is a common emitter. It is asked IC by IB. That's what is asked. Okay. Now you apply. Okay, this V dash is G0 voltage 5.3. VB is 0.6 from here to here. Okay, then you apply loop equation for this. So minus plus, so minus 5.3 plus VBA plus current times this resistance current is IA. So this IA is IB plus IC. Then IC you get 10 milliamperes. Substitute the values here, you will get 10 milliamperes. Now I want to calculate I dash. Okay, then I dash is voltage here is 5.3 volts. Here it is 10 volts. 10 minus 5.3 by this resistance. So that gives I dash as 1 milliampere. So your IB is I dash minus G0 current is IB. IB is I dash minus 0.5 that is given in the question itself. This is 0.5 milliamperes. Then you will get IB as 0.5 milliamperes. Now I want beta. So the formula is IE is equal to 1 plus beta times IB. That is reorganized as B beta is equal to IE by IB minus 1. So that is 19 is the beta. That is current gain in common emitter amplifier. Beta is 90 for this arrangement. You have one more question. The stability factor, yes, means that is dou IC by dou IC naught. It is clearly given, with respect to IC naught, collector current, variation with respect to saturation current. For the network shown here is asking, this is a fixed bias network. You remember the formula very well. This is general formula. But it is fixed bias network. Dou IB by dou IC becomes 0. So S is equal to 1 plus beta. So your answer is beta is given here 100. So 1 plus B, so 10. Your 2 is the answer. In the given circuit, what is the value of collector current flowing in the transistor? This is asking. So you have 25 volts here, then 150 kilo ohms. This you need to remember. Okay, then this current through this resistor partly flows through this diode, flows through collector, flows through the load. So I will call this current going through 150 kilo ohms as I dash I1. Okay, and this I will take say Ri. This I nomenclature it is Ri. Then the VZ given is 10 volts. This current through GNR I take IZ. Then current through collector IC. Then collector to load IL. Now I want to make one point here very clear that the current, total current, what is flowing through this resistance, that is I1, is equal to, we apply KCL here, I1 is equal to IZ plus IL plus, sorry, IC plus IL. But when compared with current that is flowing through IC, especially the transistor, okay, the current that flows through GNR diode is very, very minimal, and at the same time, the question it is not given, so we can take it very, I mean, comparatively it is very small current, so I don't consider this IZ. So I will take I1 is equal to IC plus IL. Finally, I have to calculate IC. So if any current is given through GNR diode, I would have considered it. It is neither given nor any data to calculate. Okay. So in that case, what I do, I will write the load voltage. I mean, here it is VI. Okay. Then this is VZ. This is from here to here VZ, from here to here VB. Okay, so this voltage is nothing but the voltage across the load resistor, voltage from collector to the ground also, and voltage, the breakdown voltage plus voltage from base to emitter. So because this root, these values I know, this is 10 volts, and VBA I take some 0.7. If it is not given, we will take 0.7. Some value is given, that we will take. So VI is equal to, rather I say that 25 volts is equal to, of course, first we are calculating low voltage VL here, VL. So VZ plus VBA, that is what is given here. Then VL in the problem, it is VZ is 10, it is 0.7. So your VL become 10 plus 0.7, so 10.7. Okay. Then the input current I means this current through 150 ohms. This 150 ohms is obviously VI minus VL means this voltage minus this voltage by this resistance. That gives input current 95.33 microamperes. Then load voltage, VL we have calculated 10.7, RL is given 125 kilo ohms, so it becomes 85.6 microohms. Then out of I, total current is I is equal to IZ plus IL plus IC, but IZ we ignore. So II is equal to IL plus IC, so IC is equal to II minus IL. So 95.33 minus 85.6, 9.73 microamperes will flow through 9.73. This one, 3 is the answer. So when a circuit is given and say you lack some data there, suppose for VB is not given, you take 0.7, but you cannot take the current passing through the Z some fixed value because that ranges. We don't know what type it is. VZ is equal to 10, and for now really we don't know how much current flows through this, and at the same time no data is given. Calculate IZ, so we take it as very less when compared to current flowing through IC and through IL put together, this current is very, very low. So you make it 0, then I is equal to IL plus IC plus IL, like that you have to calculate. I mean, genuine, values you can always assume, and I mean, if you take current through Gina diode, when data is not given as 0, I mean, it is just. Now, this is one common emitter. Now, forward current gain of the transistor shown is, I mean, the beta is 100. The transistor operates equidistant. Is it in, the active region or saturation region or cutoff region? If it is in saturation region, the voltage between C and E will be something like 0.2, something like that, silicon transistor. If it is cut off, then the entire voltage here will appear here. Okay, because no current flows when it is cut off, so entire voltage will appear here. So it will be 10 volts. So when the saturation point or 0 volts you can take. So if I calculate this voltage from collector to emitter, if that is something between 0 and 10 volts, means I am in active. That is what is the application follow. Now my object entire focus is to calculate what is this. This is emitter base, correct? VCE from here to here, how much voltage is that? My object is. So whatever I do to calculate VCE. Then what I do, I apply KVL through collector base terminals. This is collector base. Okay. This is what is. Okay. Yeah. Now you start like this. This is B, this is E, VB voltage. You can always assume 0.7. Okay. Then I will take after that, the I mean I can take this loop I can take, or this loop I can take. What I have taken? Let's see. Yeah. This is taken like this. This loop is taken from here, then emitter to base, then here. Okay. The current flows through this resistor is nothing but base current. So this is 10 minus 10 power 3, like 1 kilo. This is emitter, so this is RE. Okay. Minus point 7 means this voltage. Okay. Basically 10 is equal to 10 power 3 IE minus plus 0.7 plus 270 ohms, into 10 power 3. Okay. This is kilo ohm, so you have to take 10 power 3. Then IB is equal to 0. So IE you can always write, okay, 1 plus beta times IB. This entire 3 terms I take right side, so 10 minus 0.7 become 9.3. So left side 1 plus beta IB plus 270 10 power 3 IB. And in the question, beta is given 100. So you substitute that, you will get IB as 25.6 microamperes. Then IC is beta times IB. So when you multiply this with 100, you will get 2.506 milliamperes. Then IE is equal to 1 plus beta times IB. You calculate, it will come 2.55318. Then IC, I know. Okay, now what I need to calculate, I want this voltage. When I want this voltage, I should know this voltage, I should know this voltage. Then IE current going through this, I know IE is calculated as 2.5318. IC is 2.508 in this. This current I know, this voltage I know. I apply KVL in the output circuit. 10 volts is equal to IC times 1 kilo ohm, VCE plus IE times 1 kilo ohm. Then only variable is VCE. Then that's what I have done. So I can always substitute values for IE and IC straight away. Okay. Or yeah, instead of that, you did one more step. Then it's the same. You substitute IE and IC, you will get VC is as 4.962 volts. Your collector voltage is 10 volts. Roughly, in a typical problem, it will be half of this if the transistor is in active region. So even you got this as 4.962. So hence this circuit is in active region. So this is what is forward active region. I mean input bias is input junction is forward biased, output junction is reverse biased. So you have this in active region. 4 is the answer. So when you are asked to know whether the transistor is in active region, cutoff region, saturation region, you calculate VCE. Ideally, you can take VCE, SAT if it is in saturation, you can take 0. Cutoff supply voltage you can take as it is because it is open. Then active region, roughly half of this, certainly not something between 0 and VCC. Now you have one more circuit, the 3-terminal linear voltage regulator. This is series voltage regulator. We have studied, diode circuits. Is connected. This is 10 ohms. What is the power dissipated in the transistor? Power dissipation here is asked. So for that you need VCE IC. So VCE IC becomes power dissipation. For that you proceed like this. This is emitter, this is collector, this is base. Base to emitter is 0.7 volts. Then it is given 1 kilo ohm, G0 voltage is 6.6, this is 10 ohms. So what is current flowing through collector is IC. Then I said flowing out through emitter is IE. So this current going to the base IB. So I is equal to IC plus IB. What I do is I name it as X point. Okay, then the current that flows through 1 kilo ohm gets added up to IE and finally goes through 10 ohms. So what is asked is power dissipated here. Let us calculate the IC and calculate VC. Applying KVL at the input means this is VI is equal to VCE times say what VE means drop across this. Okay, this drop plus this drop is equal to VE. Basically load across the voltage across the load I am calculating. Then VCE is equal to, so Vn is 10, VE in the problem it is you take say this is 6.6, this is base emitter, VB is 0.7, so this becomes 7.3 this voltage from here to here, this plus this way. Okay. Yeah. That is not plus. This is plus minus. This is I will say minus plus plus minus. So I have to subtract 6.6 minus 0.7. We'll get 5.9. Okay. So is equal to 4.1 volts. So this current I1 through this I am calculating. I1 is equal to voltage here Vx minus VE, okay, by this resistance. So Vx 6.6, VE 5.9 by 10 power 3. So that gives 0.7 milliamperes. Okay, current. applying KCL at E. Here IA plus this I1 is equal to IL. Okay, so that is IL is equal to IE plus I1. So I is equal to IL minus I1. I1 I know, IL I know, substitute. I will get I is equal to 0.5893 amperes. I can take emitter current approximately collector current. So collector current is 0.5893. Then I calculate VCA, already I have calculated 4.1. Then IC is 0.583. Then VCA into IC, you will get 2.416 watts. 2.416, that 16 not considered here, so this is 2.416. 3 is the answer. Now you have one more question. It is a fixed bias emitter resistance. Just recall that the Q point is stabilized in better way. He is asking what is V naught. So for that I had to calculate current through this. I can always if required I can say that the IC is IE, and if I find IC then that is equal to IE, then IE times resistance will be V naught. So what I do, apply KVL from 10 volts to the ground it is through VE. So this one, to this I will apply like this. Okay. So 10 volts minus 10 power, this one 10 power 4 IB minus VBA plus, sorry, again minus 100 ohms IE. Okay, so I will calculate, I have opportunity to calculate. In the question itself, it is given VB is 0.7, I see approximately like VB. Okay, then 10 minus 0.7 is 10 power 4 IB plus 100 IC. Beta given is the circuit it is given. Yeah, it is given. DC current gain of 100 it is given. Common emitter, so that is beta. Beta is 100. So I take IC approximately equal to IE. So 9.3. This is 9.3 volts is equal to this. What I do, I convert it to IC. Means IB I will do like IC by beta. So I will get 100 IC plus 100 IC. So 200 IC. Then IC I calculate as IC is equal to 9.3 by 200. Then V naught is, this is 100 times IC, so we get 4.64. One step we have to do here, like IC you have to calculate, that is 0.0465 amperes. Okay, so like that you have to do what is asked, then by doing what you can get it, unless again I repeat, you should have done at least some couple of such exercises with emitter resistor, without emitter resistor, then you will get better grasping, you will be able to do well in the examination. So V naught output is 4.65, 1 is the answer. Then one more problem it is given, again it is a common emitter circuit. The transistor in the given circuit should always be in active region. Okay, take VC is set 0.2 volts. Okay, VBE 0.7 volts. Maximum value of RC ohms which can be used is, what is that RC value maximum you can use? What is asking? VSAT value is given, it doesn't mean that it is in saturation region. VB is 0.7, beta is equal to 100. Applying KVL around input loop, is 5 volts minus plus, so then this is plus minus, so minus this is RS, so IBRS minus VBE 0.7. So current IB is 2.15, milliamperes. And what is asked is uh, the maximum value of RC. Then what is IC, beta times IB, 0.215 amperes. Okay. Now apply KVL in the output circuit, means 5 volts minus ICRC CE, okay, is equal to 0. IC 5 minus ICRC minus VCE is equal to 0. Then VCE IC, VCE becomes is equal to 5 minus 0.215 RC. For active region, VC should be more than VC set. So this value 5 minus 0.215 RC more than 0.2 be in active region. So apply this and calculate. Finally, this RC should be less than this minus 0.215. We will get 42.32. We should have the RC actually in the percent. Minimum it should be that much. It could be more also. Any options are given. So RC minimum is 22.32, but in the percent, I think there is some mistake here. Not maximum, it is minimum value. With the given data, you cannot calculate RC max. You can calculate RC minimum. There is some problem with this. Then you have one more. It is a voltage divider bias. Current IC is given 2 milliamperes, VC 12 volts. Then is asked what is the value of R1 and RC. It is basically a design problem. We have to calculate what is R1, what is RC. For DC analysis, you open these two capacitors, then your DC circuit becomes without these capacitors. 25 volts, 2 resistors here, 2 resistor transistor, that's all. Okay. Now we have to calculate what is R1, what is RC. Okay. So here, let us go ahead. VE is equal to, this voltage here, IE RE. Okay. IE RE approximately to IC RE. IC is given as 2 milliamperes. So VE is equal to 10 volts. Here voltage here is 10 volts. Okay. My objective is to know what is the voltage across this and current, then I will get RC. So in that direction I have to work. Then VB, here VB is equal to what is the thing? VB is equal to VBE, means from here to here plus VE at this voltage. So this is 0.7, this is 10, so 10.7. Then this voltage is 10.7. Then I calculate this, I know this voltage equal to, using voltage divider bias, I will apply that voltage divider formula here. So VB is equal to R2 times VCC by R1 plus R2. VB I know, VCC I know, and R2 I know. Then you just rearrange and finally you will get R1 is equal to 26.73. It is one of the design parameter asked. Okay. Now I want to calculate the RC. RC, this one. So VCC. Suppose I take this as VC. Okay, and say VC is equal to VCE plus VE. Okay, so that's what is written here. RC is equal to VCC minus VC by IC. Then RCC, VCC minus that VC is VCE plus VE by IC. VCC I know, and VCE is given 12 volts. Then I have calculated VE as 10 volts. So 25 minus 22 by 2, is it? So this becomes, we will get 1.3 kilovolts. This, yeah. So this is what is asked. What is R1? What is RC? That's how we are doing. So one more problem: the Zener voltage of a Zener diode is, you have one diode here, 3.3 volts, and the base to emitter voltage, base to emitter here, base to emitter here. Assume that both the transistor of same type, say silicon, type number same. Then the low voltage of the voltage regulator shown below. I mean this voltage. Then the low voltage of shown below is, we check this point 7. If we want to know what is voltage here, I mean Zener voltage plus this voltage. Like so. So what I do, that V out, this one I do like this. V out is equal to, I go like this. Vz, then VBE, VBE. This is graph. So V out is equal to VBE plus VBE2 plus Vz. So all values we know, substitute 4.7. What you get is here with respect to ground is 4.7. Problem looks at the outset it's complicated, but it's very straightforward. This voltage you know, then this voltage you know, this voltage is you know. So this voltage is equal to this voltage plus this voltage. Simple. Now you have one more problem. The output voltage of circuit is, this voltage is asking. So this is base, 5 volts is given at the base. This is NPN, PNP. This is N, so 5 volts. At least part of it will come here, so it gets reverse biased. I mean, it will be the cutoff region. If that is the case, I will redraw the circuit like this. This one only, this transistor is off, so I remove this part. This one. So what is asked is the V0. So for that, what I do, this 5 volts is equal to 5 times IB, okay, plus 0.7 plus this is IE. I can say actually 2 times IE in kilo ohms. So current will be in amperes. If it is in ohms, that will be okay. 2 into 1 plus beta IB. Then you calculate, substitute all those values. You will get this much. Then beta is given 100. Then 1 plus beta times IB is equal to IE. Then IE is this much. Calculate. Then V0 is equal to this voltage times this current. This is in kilo amperes. Sorry, kilo ohms. This is in milliamperes. So multiplication of 2 into 2.09 gives 4.9. This is the voltage. Here also it looks a bit tough problem, but if you analyze little, then this transistor goes out of your analysis. Then beta of a transistor with respect to temperature, will it increase, will it decrease? That's what the formula, the power, collector power, an IC square, like resistance, then IC is equal to beta times IB. Okay, temperature increases, then power dissipation across the collector junction will increase, which leads to increase in collector current. Okay, so collector current is beta times IB. So when the temperature is increasing, collector current is increasing. So your the beta will increase. Generally, base current, because no additional data is given here, to assume IB is equal to constant. So when IC increases due to variation in temperature, that is sure it increases, so beta increases. So the answer is like increases with increase of temperature. 2 is the answer. Beta increases. In effect, is a better chopper than a BJT because you have to with a conceptual problem, perhaps one more problem. To turn on BJT, a minimum of 0.7 volts at the input diode, that is VPG, is required. But in case of FET, no such type of offset voltage is required. Even VG is equal to 0, it's a channel from source to drain, so it starts conducting. Chopper means there should not be any, I mean, you need to voltage some finite voltage at the input junction to switch it on. But in case of FET, it's not required. So it is, FET is a better chopper than BJT. The reason what is asked is it has low offset voltage, almost zero. In case of BJT, it is 0.7. Okay? This is again one problem. One minute, please. The common emitter amplifier shown in figure is biased using 1 milliampere current. The emitter. The approximate base current value is, what is this base current is asked. What I do that beta value is given and IC value is given. IC means approximately you can get IE as IC. So 1 milliamperes. What is beta is given? Simply is asking IB. So beta times IB is equal to IC. So IB is equal to IC by beta. 10 milliamperes. 2 is the answer. So these are the medium to complex, highest complex level of problems. Except one of the problems. So most of this type of problems you find in the GATE exams, more and above illustrative examples I have given while doing the presentation. So with this, the GATE problems on biasing stability have completed. Now I'll go to the BJT amplifiers. Actually, what I supplied material from here it starts from the 6th day. So here, what is important is the various small signal models for low frequency analysis, high frequency analysis. There we need to find, the current gain, voltage gain, impedance, output impedance, current gain and voltage gain, including the source resistance. Like that we have to do. And a lot of derivations are involved. I'll go through the derivations a bit fast. The objective is not to educate you how to do derivations. You have done in detail. Only thing you have to refresh the derivative process. Then finally, you have to remember the end results for various parameters. This formula you have to. Okay. So in this unit, we learn about AC response of transistor using different transistor models. 3 models we use. One is H parameter model, also called hybrid model. That we use only at low frequencies. And RE, there is one RE model. You can use at low frequencies and high frequencies. But in our discussion, we use it at low frequencies. And we have one high model. You can use even at low frequencies, high frequencies. Both we'll discuss here. So before the invention of H parameter model, RE model was popularly used. Subsequent H parameter model became popular. So most of the times we use hybrid model for low frequency analysis, that is H parameter model. For high frequency analysis, we use pi model. They're very handy. Anyway, the pi model we do at low frequencies also. But everything is small signal analysis means amplifier circuit analysis we do. Large signal applies to power amplifiers. That's what is meant. Large signal amplifiers are power amplifiers. So it is small signal. So in the one of the last classes, you know how to draw, load line. You have refreshed your mind. DC load line after that, AC load line. AC load line will be steeper than DC load line. When you apply AC input current for zero input current, obviously the Q point, rather I put it like this, your DC load line and AC load line intersect at the Q point, indicating the meaning is that when input is zero, obviously what load line, AC load line has to go through the DC Q point. So obviously that Q point is same for DC load line, AC load line, but AC load line will be steeper. Okay, so when we apply input AC signal, the Q point moves from DC Q point along the AC load line. This side, that side keeps moving based on whether the input is voltage positive or negative, whether it is common emitter or common base or common collector, like that. So because input signal variations are small, obviously now this is an amplifier what we are talking about. The output signal will be large, no doubt, but the movement of Q from the center on the AC load line is minimal, unlike in case of power amplifiers. Power amplifiers will design in a way that Q point almost goes to saturation, one side, other side almost goes to Q point, but still it should be in active region. Otherwise, the output signal will be distorted. Because of distortion, we'll have a lot of harmonics in the output. So, for power amplifiers also, transistors should be in the active region, but the signal, input signal variation, large signal that is. Okay, even output also varies in a large fashion, going close to saturation on one side and close to cutoff on the other side, but still it will be in the linear region. It's very wonderful photograph. This is emitter, base, collector. Small signal is defined as a signal having magnitude sufficiently small to keep the transistor in active region. Certainly, in active region even for power amplification also, but we have various type of power amplifiers like A, B, C. When we go there, we will discuss about them. Okay. Here we discuss transistor as amplifier. This is a general, amplifier circuit with voltage divider bias. This is the voltage you are expected to amplify. Then this is source. This is source resistance R is suppose. This is R1. This is nomenclature R1, R2, RC, RU. You have one coupling resistor, a coupling capacitance to couple the input voltage to the base. You have here one more coupling capacitance to couple the output voltage of collector to the node here, and you have a bypass capacitor here across RE because if it is not there, there will be negative bias, negative feedback, so gain will be less. So when we are using this as an amplifier, if you have RE for DC analysis, it will stabilize operating point. For AC analysis, there should be a capacitor across this, but the frequency of operation, we have to see that its reactances are almost zero, so we short them. When we short it, then this gets bypassed. Okay? And this is straight away connected out to source is connected to base. Then for DC analysis, earlier we have seen we open the capacitors. Okay. Then for DC analysis, we close the capacitors and we ground the DC supplies. We make this ground. We ground it. Then only we can do AC analysis. You can as well apply superposition theorem. You can do DC analysis, calculate collector current. You do AC analysis, you calculate collector current, then total current is like IC plus small IC, that capital IC is DC current, small IC is AC current, and because you have a capacitor, DC gets blocked, only AC gets up. So here we have seen DC analysis enough. Now we will see AC analysis. For AC analysis, all the capacitors are short circuited, okay, including the bypass capacitance, and your the DC supplies will be grounded. We are basically dividing the analysis into two parts, AC and DC. For DC becomes DC voltage will become zero. Uh, that's what I was telling. Like coupling capacitors, bypass capacitors, all these things. What you have to do here for AC analysis, first you take the AC equivalent circuit, then you replace the transistors with its low frequency model, whether it is H parameter model, RE model, or I model, whichever you got all, we'll see all three. So, see, first, with respect to these resistors, you arrive at the AC equivalent circuit. After that, you replace the transistor with the model, H parameter model, or RE model, or Y model. So that's what is to find out AC response of the circuit. We need to do two things: obtain AC equivalent circuit, replace the transistor equivalent circuit. That's what I was doing. This is what is step one. You do like this: short circuit the DC sources, means earth them. Okay. Then short all the capacitors C1, C2, C3. Okay. Then redraw after doing step one and step two. Step three is redraw the circuit. Then you will get like this. Now this is RS, source resistance. Okay. Then R equivalent is R1 in parallel with RP. When you ground this, it will come this side. So R1 come in parallel with R2. Then RC gets grounded. Okay. RC gets grounded here. That's what is shown here. Here you see it's grounded. Then RE gets shorted because capacitor is get shorted this way. Okay. So this is AC equivalent circuit, keeping the transistor symbol as it is. Now, which model we apply? We go ahead and work out with various small signal models for transistor. A small problem is there, gate. It is conceptual problem. If the emitter resistance in a common emitter voltage amplifier is not bypassed, what will happen? This is what is asked. This is not bypassed. Then even the AC signal feedback, negative feedback will be there, so its gain will go down. The very reason why we have bypass capacitor is we have the sufficient amplification factor for the transistor. If it is not there, gain of the transistor will be overside. So that is reduces voltage gain. Actually, when you give negative feedback, input impedance will increase. So the answer is reduces voltage gain and increases input impedance. Voltage gain never improves with negative feedback. Both never. So your answer is B. This is a very, very conceptual question. Now, this concept you should have in your mind. The equivalent model of transistor. Three models are there. I was saying that hybrid model for low frequencies. Then RE model. Okay, this is one model. This is also called H parameter model. We have hybrid pi model. This we say hybrid because the parameters units are different, not all like ohms or constants, not like that. Some parameters ohm, some parameters like conductance type most, and some parameters constants, current gain, reverse voltage gain, like that. But that's why we call hybrid parameters. H parameters are hybrid in nature. Similarly, RE parameters. So for low frequencies, we apply hybrid model or H parameter model. Then we can apply these two models for low frequency as well as high frequency. Let us go ahead working on H parameter. All the three models are used for small signal analysis, for small low frequency and high frequency. Then we talk about hybrid model. It is also called H parameter model. It is widely used before popularity of RE. I mean, working on RE model is simpler than H parameter. Less number of parameters are there. This analysis using various types of models is very tricky. RE parameter model is simple. Obviously, in the results you will have error. Then you have to calculate that error. If it is small and that is tolerable in the given application, you can always go for RE model. No, that is error is large because of simplicity of the model. Then you can work on H parameter or hybrid pi model. So parameters are defined in general terms. I mean, transistor you can configure in common emitter configuration, common base, common collector. But when I am doing analysis, finding the various parameters like current gain, voltage gain, input impedance, output impedance, current and voltage gain, including the source, I will take the general transistor configuration. I don't say anything. Generic way I will work out, and then they are applicable for any configuration. And also I will give one slide on how to convert the H parameters from one configuration to another configuration. These are hybrid model. This is hybrid model because the parameters have mixed dimensions. That's what I was telling. So hence hybrid parameters. Need for hybrid parameters. Yeah, earlier Z parameter type, Y parameter type analysis were done, especially in the inputs were there. It's not that serious topic. So they were not directly applicable to semiconductor transistor. So they have gone for a model. So that's how the parameter work. Now I'll take the amplifier as a two-port network. The input port voltage V1, current I1. So output port current I2, voltage V2. Here, that's what other day, some time back I was saying total current or voltage is AC value plus DC value superposition. But here we do AC analysis. Okay. Out of 4 parameters V1, I1, I2, V2, we do like this. 2 parameters we take dependent and 2 parameters independent. So independent parameters I will take input current and output voltage, that is I1 and V2, and then your V1 and I2 I will take as the dependent variable. So I1, V2 as independent variables, V1, I2 as dependent variables. That's what is written. V1 is equal to function of I1, V2. I2 is function of I1, V2. These are all independent variables, and V1, I2 are dependent variables. When I write, like for the input side, I can write like this. Using H parameter, I will draw more detailed circuit diagram later. Including H parameters, I will write like this. V1 is equal to, this is I1, this is V1. V1 is equal to H11 times I1 plus H12 times V2. Okay. I have to write in terms of I1, V2. That's what I have taken I1, V2 as independent variables. So V1 is something times I1 plus something times V2. Similarly, I2 is equal to something times I1 plus something times V2. And I will take those proportionate constants as H11. This first suffix shows input port. Then the next one, if it is 1, it is input again. Here it refers to input port, this becomes refers to output port. This is value something between input and output. This is purely input parameter. This is again input output parameter. This is output parameter. So I2, H21, I1 plus H22, That's how we write. Then now we define these parameters which are called hybrid parameters. H11, now what I do, V1 by I1 when V2 is equal to 0. That's how I define. H11 is equal to V1 by I1. Okay, when this is H11 is, V1 by I1 is input current by, input voltage with current, something like impedance to use. When the output is shorted, H11 is not input impedance, it is the input impedance with output short circuited. If you say the H11 is input impedance, meaningless. When output is shorted, when you want to calculate H11, invariably you have to short the input and calculate. So, because this is purely input parameter, I can say instead of H11, I can write HI. Okay, HI. So H11 I call HI. Then H21, this one, this is I2 by I1 when V2 is equal to 0. This is the current gain H21 when the output is short. This condition is very, very important. So H21 can be represented as say HF. I will represent. Okay. Then second one is H12 is H12 is V1 by I1. V1 by V2 when I1 is equal to 0. I1 is equal to 0 means input open circuit. Okay, this H12 is V1 by V2 when H12 is reverse voltage gain. V2 by V1 is voltage gain. V1 by V2 is reverse voltage gain. When input is open circuit, I1 is equal to 0. Under that condition, I am getting this one. So I can name it. This is something between input and output. Say I will write HR. Then H22 in the equation is H22 is I2 by V2 when I1 is 0 means input is open circuit. I2 by V2 when H2 it is current by voltage. It is if the input is impedance, output reverse is admittance. So H2 is admittance factor with input open circuit. So I will call this H22 as H1. So H parameters arrived at H11 as HI, H12 as H12 as HR, then H21 as HF, okay, H21 as HF, then H22 as H0. So these parameters, hybrid parameters, for these four hybrid parameters, that second suffix, if I add E, that becomes common emitter. If I add B, that becomes common. If I add C, that becomes common. That's what. For common collector, H parameter HI becomes HIE, HF becomes HFE, HR becomes HRE, H1 becomes HOE. Like that, even for common collector, you can write common base. So the analysis is general. At the end, you can make it specific based on the configuration. Now, when this is the thing, this is the input V1 is equal to H11 times I1 plus H12 times 2, and I can draw the input equivalent circuit. The model for this equation is V1, I1 is for going to H11 is HI, okay. Then this H12 is HR, so V2. It's kind of HR is a most units it will have, so V2, then it will become current source. So the input circuit for the transistor, we are now working out on models for transistor, H parameter model for transistor. So this equation, you can convert into a model like this. Then the other equation, I2 is equal to H21 I1 plus H22 V2. Then I can, I can model this equation like this. This parameter, I will replace this with specific parameter. It is equal to h of I1. Your hf is a constant, so h of I1 is a current. So you have a current source magnitude h of I1. Then uh, this one h naught is MOS, means okay. So uh, current source will have its source resistance parallel to it. So you can take that as the the H naught, then output is V2. This current is I2. So from the equations, you can model the input circuit of the transistor like this, or like this. This is a ground, this is a ground. Then you now mix up this input and output together for the whole transistor. You can whole transistor you can show like this. This is input circuit, this is output. This is H parameter model for low frequency model. Of course, H parameter model we use only for low frequency analysis. This is transistor. When you are analyzing the circuits involving transistor, say that analysis is AC analysis, you have to replace transistor with its equivalent models like this. Okay? So that's what is written. This we have already discussed this nomenclature. Now we do now the AC equivalent circuit. Earlier, whatever we have drawn plus this one. Okay, analysis of transistor amplifier using H parameter model. This is the transistor. Okay, this is load resistance. Okay, this when we have drawn AC equivalent circuit, keeping the transistor symbol as it is, we have an RP here. For analysis, you can take it very high, so you can open it to make the analysis simpler. You can have it, then you work out the source. This model you can work out. You can have RB here, then circuit left side can work out like this. So I say that your RB is observed in this resistor. Okay, and accordingly voltage source is also modified. So not to complicate things, I merged my RB here, source resistance, and finally this is the equivalent source, voltage source. Okay. This is I1, this is I2, okay. This is voltage source HRV2, this is plus minus V1, this is plus minus V2. Current flows inside, that's a part we have shown in the model. So IL is opposite to I2 that passes through the load resistance. When you see from here, it is output impedance. When you see from here, it is input impedance. The gain, if you calculate from here, it is omitting the source resistance. If you calculate gain from here, then including the source resistance. Both we do, whether it is current gain or voltage gain. So let us work out now these parameters. One, input impedance. This is ZI. Output impedance. Current gain without considering source. Voltage gain without considering source. Then current gain, voltage gain considering source. The 6 parameters, derivations will go through fast. And the process you can easily understand, but what is important is remembering the formula for 6 the parameters. Okay, you can say performance parameters of an amplifier, and the detailed formula you have to remember. The gate, if the data given is not sufficient, you can approximate that formula, reasonably apply it in solution. And even we work out on simple H parameter model also. How it is done, I'll show it later. Simpler model than H parameter. That is also, I can say, approximate H parameter model. When you apply that model and calculate all the 6 parameters, and we calculated the error, before calculate the error you use because of simplification of the model, compare that with full model, H parameter model. If the error is limited based on the application, suppose application take error of say something like 5%, and the error is less than 5%, you can always hold it. like small signal model. Small signal model reduces your analysis a lot. So actually in engineering, in many places, it so happens that the analysis looks very complicated. You can make reasonable assumptions and simplify it and work out on that. And full model also you work out and see the error introduced because of approximation of the analysis, and it's making the analysis simpler. Then errors will be very marginal, which a specific application can take. So in that case, now when you apply full model, do analysis, if it takes 10 hours, you apply simpler model and do analysis, it may take 2 hours. The error is something like 2% application can take. What is the point in going for a full model and do all that analysis? It is just academic interest, no practical interest. Okay, so it should be you being the engineering, say a student or graduate, it should be very, it should be effective, not that something is given, you keep working on that in a very elaborate way. In a simpler and reasonable way, you are expected to work and get the result. It cuts down time work. But the error you do because of simplifying the models, that will be very minimal. That is acceptable in the specific application. So now we start calculating all those parameters, performance parameters of amplifier. This is the previous one. Only I introduce here. Then I1 is input current. Then I2 is current flowing through. So IL is in opposite direction. What you want is output current by input current. IL by I1, that becomes current amplification. Your I2 is minus I2. IL is minus I2. I2 flows this side, IL flows this side. But magnitude, both are same. Okay? Then this current is current finally passing through this and because this simpler model will work out something. This is very high value, so you can always it's not a small, but the inverse of that resistance is very high, so you can work on it. Here your HR value is going to be very small, so total this value is very small, so you can always neglect this. So HI here and this source here. So this source and this parameter go off. Okay, that's how we work. So voltage drop across RL is V2. Okay, that is V2 is IL by RL, that is minus I2 RL. Then apply this special what I want is IL by I1. Okay. I2 is HFI1 plus H0 V2. That is equal to HFI1 plus H0 minus I2 times RL. By solving the above equation, what you want is I2 by I1 plus IL is minus I2. From this equation, you get this V2 I replace with I can straight away write ILRL, then but here we have I2, that's why I have written I2, then minus sign I will take accordingly. I2 by I1 I will get HF by 1 plus H0 RL times, but IL by I1 becomes minus, so minus HF by 1 plus H0 times RL. This is the current gain, okay, without considering the effect of the source from this to when we consider RS. Okay? So this formula you need to remember, and it is valid for all types of configuration. If it is common base configuration, it will become minus HFB by 1 plus HOEB times R. Like that. Then input impedance, we calculate input impedance nothing but the input voltage V1, current I1. So this input impedance is this voltage input impedance times current flowing through that. So that's what is written. V1 is for I1 Zi. So V1 by I1 gives Zi. So it is again equation 1 means that hybrid equations what you have written. I1 is V1 is equal to HI I1 plus HR V2. Then I will replace HI1 plus HR. Beta replace with minus R2 RL. Then the V1 I have, I1 I have, this I2 I can transfer it into current gain. Means I will like minus I2 rather I2 by minus I2 by I1 is minus AI. So accordingly, that's why AI appears here. You bring out, you substitute like that, and you will get V1 by I1. I2 goes when you replace this with I1 times VI. So that ZI, that is AI, that I1 bring other side. So V1 by I1 becomes HI plus VI current gain times HR current. So this you when you replace this CI value, that is this one, the equation, you will get ZI is equal to HR minus HR times HF times RL by 1 plus HVRL. The it is better to remember this equation than this equation, simpler one. Replacing AI with the previous formula, you will get this one. It is up to you what you want. Then voltage gain is your V2 by V1, that is V2 means V0. This one is this V0. No, V0 by V1 nothing but V2 by V1, and V2 is minus 2 times RL by V1. Okay, multiply and divide both sides with I1, then minus I2 by I1. This is current gain here. This becomes V1 by I1, that becomes ZI times RL. So your input impedance is current gain times RL by input impedance. This you can remember, or you substitute values for AI and ZI, you get something. CAB is equal to minus HF times RL by this one, where this is a delta H, or is HI times H0 minus HR times H. So that is the value for what it is. It is actually a constant without any units. So this is in ohms, mhos, this constant. So sometimes constant value. So I mean, if you write this, it looks too big here, so that's why it is written. Just a symbol is used. Then output impedance, looking from here, that is V2 by I1. Okay, so Z when uh, to calculate Z0, we need to short input source. This we have to short and open the output terminal. This we have to know in the short it. I mean, without considering, say, okay, you short this voltage source, short it. Okay, then RS comes into picture. Then Z0 is V2 by I1. Then Z0 is V2 by okay, V2 by I2 equation is written here. I2 equation is HF, I mean this current flows through this plus this. So HF I1 plus H0, the voltage across this V2. Okay. So now apply KVL in the input loop. Means you have to minus minus I1. So I1 is flowing this side. Minus I1 goes this side. This is shorted. Minus I1 RS. Okay. Then minus I1 HI. I mean current leaving in the nodes into 0. This is I1 HI minus KVL I am applying. Voltage around the loop. Okay, minus I1 RS minus I1 HI minus HR V2 0. So that is the case. I1 becomes minus HR V2 by RS plus HI. Okay, and substitute this equation in one, that's this one, you get RS plus HI, then delta H, the parameter, simplification we have done like this, then plus H now times RS, this is the output impedance. Now, overall voltage gain considering the source means V2 by, yes, earlier it was V2 by V1, yes, V2 by Vs. What I do, multiply both sides with multiply V1 divided with V1. So now V2 by V1 is AV. This formula you know already. AV is equal to AV times V1 by Vs. Then the input circuit you can do the entire input circuit here you can replace with ZI. So you get this RS in series with ZI and then back connected to source. Then what is required is the voltage across AVS is equal to AV times V1 by S. Okay, this is V1. So voltage here I can write V1 by Vs is ZI, okay, by RS plus ZI means simply V1 is equal to ZI by RS plus ZI times Vs. So V1 by Vs is equal to ZI by RS plus ZI. I substitute this value here. I will get, this is the formula. Suppose source is ideal. Current source, voltage source, when we say it is ideal source, RS is 0. Okay, so if that is the case, RS is 0, then your voltage gain considering the source is again 0. So, in practice, the voltage source will have series resistance, and similarly, ideal current source will have infinite impedance across it parallel to the source, but practically will have some high value. Okay? So similarly, we work on the current gain including the source. So I2 by IS, basically you want the I2 by IS you want. Consider. So both I will multiply and divide with I1. So first I will write I2 by I1, then I1 by IS. I2 by I1 is CI. Then I have to calculate the current. Again, the input I can transfer the. You need to this is source. You can convert this into current source. Then you can arrive at this solution. This one becomes. IS. I'll show here. You will have a current source here. Across that you will have RS. Okay. So if that is the case, and of course ZI is in parallel with RS. So I1 passing through the RS is I1 IS times RS by RS plus ZI. That's how we calculate the current. So that is equal to RS by RS plus ZI. Plus that I1 by S with RS by RS plus ZI. This will get. For I was telling ideal current source RS, source resistance is infinity. So what you do, you divide the numerator and denominator with RS, then you get 1 by 1 plus ZI by RS. RS is infinity, so ZI by RS is 0. Then AIS becomes okay. So these are the 6 parameters you have to work out and you have to remember. My suggestion is always like remember the formula in terms of the formula already derived. Suppose AI was already for derived, ZI was derived. So better remember easier way. Similarly, the previous AVS is equal to AV. Like this. Similarly, Z0 is equal to you can like RS plus HI. I think this better than this. Like that, here voltage gain like this AI into RL by ZI. You should know what is AI and ZI. ZI, you leave it at this position, you remember what is AI. Like that. So this is the analysis, H parameter analysis. small signal transistor analysis using H parameters, and we are with six performance parameters, and they're all applicable to all configurations. It's common emitter ZIE by ZN, as per GD. Second suffix. So, overall current gain we have seen now approximate model for hybrid approximate model. I was explaining that this HR value, I show HR will be very small. So HO is very high. So it is open circuited. It is shorted, source is shorted. So you will get, that's what it's given here. It is shorted. It is open here. This is load resistance. So your simpler model is this. Of course, this load resistance is from external source. So your H parameter small signal model is this one, and applying this you can easily do analysis of transistor amplifiers for small signal, and your work will be much less than when you consider full H parameter. So now you can do on the same lines what we have done. You can arrive at all six parameters, okay? But or you take those six parameters, what you have approximated, that perhaps you can substitute there. You will get it. Better you do fundamental way and arrive at the formula. Now, generic configuration we have done. Conversion formula has summarized here. How to convert CU to CB. I want common base parameters. I know common emitter parameters. These are all the formula used. Okay? From common emitter to common collector, common base to common collector. This conversions. Now, RE model, it is simpler than H parameter model. This is transistor, okay, base, collector, emitter, and say NPN type. When this is symbol, if I replace the symbol with the semiconductor bar, NPN, this is IB, this is IQ, IC, and basically I'm splitting this transistor into two diodes connected back to back. This is base, emitter, collector, base, emitter. So this diode is across base and emitter, that gets forward biased. This diode is across base and collector, that gets reverse biased for keeping the transistor in active region. It as an amplifier. Okay. So between B and E, I will get a forward biased resistor. Between B and C, I will get a reverse biased diode. Between B and E, I will get forward biased diode. Okay. This is the textual information to calculate RD, that is dynamic resistance of the diode, delta V by IB. In our case, if the diode is between base and emitter, that you can call it as an RE. Okay, and this is the total current equation for say the transistor, beta times IB plus other IC times 1 plus beta times ICPO. This we know. The output resistance you're supposed to calculate taking both from the output characteristics. Okay, low, these are the outputs almost parallel, so your slope is infinity, so your R0 output is 0. So this is the formula fundamental formula used for calculating dynamic resistance of a powered by diode. This is input characteristics. These are all output characteristics of a transistor. For diode, you will have one. For transistor, you can have the in value for DC. So between base and emitter, you have a one forward bias resistor. Okay. Then from base to collector, it is reverse biased. There current C flows, that is IC is equal to beta times IB. Then what is R naught is in parallel with the output points output. So this is VCE. Okay. Uh, then I will replace the output uh, transistor, which is diode, which is reverse biased. Now I replace with the current source. Then the input diode, which is forward biased, I'll replace with its forward mode as a dynamic resistance in AC model. Okay? That's what is done here. Current source, then this is forward resistance RE, because it is from base to emitter, that's why it is named RE. That formula is 26, actually VT by IE, 26 millivolts will get VT at 25 degrees centigrade. So RE is this one. So for a given transistor, I will be given beta, then you can identify, arrive at collector current when this current is known. Then you can calculate the dynamic resistance. Okay, so this is your final model, and this always you can make it infinity. Here we are showing 1 by slope is infinity. So it is the slope is 0, then parallel, so slope is 0. So 1 by 0 becomes infinity, so you can open this one. Just okay. So for input 1, how we arrive at this, we are going to explain. Remember this, that is good enough for your gate exam. The current equation for diode forward diode is saturation current times e power Vt by tau Vt minus 1. Then Rd is Vd by dynamic dVd by dId, but in reverse way I'm doing dId by dVd. Then differentiate that with respect to, I will get this one. I can, when eta value is not given, I can take 1. Then dId by dVd, actually dVd by dId is Rd, so 1 by Rd. Then substitute that. Then finally I will get this is ID plus IS. IS is reverse saturation current. It is small value, so you can get 0. So ID by VT. Then RD is VT, V suffix T by I suffix D. VT at 25 degrees centigrade, calculate becomes 26 millivolts. So 26 millivolts by ID, but in our configuration, ID is IE. Okay, so RE is equal to 26 millivolts by IE. So for this derivation, we have taken this equation and worked. But for gate, remember this, that what is here now, this is the common emitter configuration RE model. It is always wise to isolate the input circuit and output circuit. This is input circuit, this is output circuit. So I want to segregate input and output. Two parts I want to make. That helps a lot for analysis and for so many things. So for that, I do little bit of analysis and arrive at that model. So what I do, whether the current flowing through this is IE. I want to bring this point of current source here. Then accordingly, I want to so it's equivalent I have to find. For that, there is work like I is equal to IB plus IC. I is equal to beta IB, then write I is equal to IB times 1 plus beta. Accordingly, using this one, I can dot across R is RE IE is equal to RE I is IB times 1 plus beta. Okay, so in that case, I will write this as RE times 1 plus beta into IB. Okay, to separate input and output current, which take RE and 1 plus beta together, and IB is the current flowing through the resistor. In place of RE, I will write RE times 1 plus beta. Okay, then instead of IE, I write IB. That's what I'm going to do. Here you see. Now, the current going through this one is IB, but its value have increased to 1 plus beta times R. Now I have separated this input circuit, this is the output circuit. And at the output side, we have a dependent current source and a resistor R. Therefore, the final equivalent RE model for C configuration is like this. R naught you can always open it. For detailed analysis, you can keep. Okay. You can even further simplify this because beta value is high, like 100 to 400, 600 sometimes. Sometimes it will be less than even 50 also. This is the full factor. Suppose beta is high when compared with 1. Generally, when beta is more than 10, you can always neglect 1. So you can even beta also you can write as you like. So this is beta IB, then this is R naught, this is infinity actually. So that's what is for common base. Similar here, this is 1 plus beta RE, this is IB. For common base, the current what that comes is IE, so simply become RE, this current is alpha IE. In the previous case, it is beta IB, it is alpha IE. Parameters change. Again, here the slope is 0, so this resistance here is high, that's why it is removed. Here also you can as well remove, but R naught for common emitter is compared to less than R naught for common base, so that's why it is totally removed here. It's kept there. It's kept there. Hybrid pi model. We have hybrid pi model. We now see the low frequency analysis. After that, we will go to high frequency analysis. This is widely used because you can use it for high frequency small signal analysis, and you can also use it for low frequency signal analysis. Okay. At low frequencies, here you notice the difference between high frequency model and low frequency model. In the transistor, you have junctions, two junctions. Okay. At low frequencies, you can always neglect or rather ignore those junction capacitances. But at high frequencies, that will come into picture. Those junction capacitances will come into picture because the reactance or in general the impedance of any capacitor is 1 by j omega C, and of course you will have resistance parameter by omega. It is when omega is low, its impedance is high. So in that case, just open them. So for low frequency analysis, capacitances we don't show the capacitance in the model, but for high frequency you have to bring them. Otherwise, if the frequency of the input is high, that's what is written here. At low frequencies, assume the transistor response. Okay, it's a bit of the working of a semiconductor is explaining here, but what I said that you take in a local fashion. So for low frequency model, you open the capacitances. This is the total model, pi model. Like it is like pi. So this is pi model. These are all the junction capacitances. This one and this one. For low frequency analysis, you can open them. Okay, and I mean for convenience, this is redrawn here, and one inside node is taken for convenience. This RB is taken as RBB dash because between B and B dash. Similarly, this is R pi. I have written the resistance between B dash and E, B dash and E, and this I have taken now C E. Okay. Then this is I would have written like B dash C, B dash E, but because there are only two capacitors, simpler notation I can use. This is CC, then this current is equal to GM times V B dash E. This is B dash E, what voltage is there, GM times, that is conductance, transconductance, VB dash U, current source. Then this one I have written CE. Just nomenclature is changed, but otherwise it is same. Okay. These are all the parameter explanations. At high frequencies, parameters like junction capacitance come into picture. At low frequencies, you can open them. CU, the original model, CU, this one is talking about. These parameters are referred in the next slide for explanation. CU, this is the capacitor which represents early effect and it is of few picofarads. Then C pi, C pi is this one. For gate, you're supposed to remember the formula. Derive the formula. If you remember those formula, it will do. Okay. So R pi diffusion capacitance that represent minority carrier storage in the base region. Its value lies between 1 picofarad. Then RP, this is this one, RP small value which represent resistance due to base connection and other resistance like base spreading resistance is also included here. As it is small, we can replace it by short circuit, otherwise you can retain it and calculate it. R pi. R pi is this one. R pi input resistance between base and emitter terminal. This formula you need to remember, R pi is equal to beta times RE. We are linking RE model with pi model. Even you can link pi model with H model also. You can do that mapping of parameters from here to there later. Then R mu, Ru is this one. So Ru is given. Resistance between base and collector terminal is very large, hence replace it with circuit. Now I talk about small signal model and we arrive at the formula for these various parameters. This is the resistance between RBB dash means this nomenclature I have taken. I opened these capacitors because we are talking about low frequency model. So you will boil down. Just remove capacitors, you will get this one. Okay. Then we have to calculate what is this RBB dash, what is RB dash E, RB dash C, then GM, B dash E, RCE, formula we have to arrive. That is analysis. Okay. So for easy analysis, I imagine one internal node called B dash. So with respect to these nodes B, B dash, C, E, I'm naming these components. This is IB, yes, okay. There's IC is this is IC. IC is GM times, this one. This GM times V dash U. Okay, and it is very high value. So imagine that no current flows here. So that current flows. Okay. Then ICGM, what is B dash is IBRU. So finally, HF is defined like IC by IB. Replace that or B dash E means or B dash E. This one we get HFE by GM. So this is the formula. We are linking pi parameters with H parameters, and this is source. This is GM value. That formula we subsequently see formula this also. This is absolute value of collector current by thermal voltage. Okay. So I can leave it like this or substitute for GM this VC by IT. You can get this one. Okay. And G B dash is inverse of R B dash E. Anyways, you can do. But one formula for each parameter is remember. Okay. Similarly, HIE, this base spreading resistance RB, RBB dash, RBB, then I mean this one here. When this nomenclature is used, that becomes uh, RP and RBP. This is input impedance HI. We are linking H parameters with RBB dash plus RB dash. RBB dash plus RB dash. This input impedance from here. This plus this. Okay. From that RB dash, we know HI, then you calculate RBs or B dash. Okay. So RBB dash is HI E minus RB dash E. That's all. Yes, you can write. Then GCE means RCE inverse of RC. This is RCE. 1 by RC is GCE. I mean, subsequently after we get the formula, we can inverse it. No problem. Then you find out current, collect current where all it is going in circuit, 40 here, 40 there, 40 here. So all this current is equal to reaching current is equal to leaving currents. That's what is written here, like we see by RC. Okay, so finally, what we need to know is GCE. Okay, uh, finally, you work out on that, you will get GCE. HR, see, uh, or RCE directly, perhaps it is. GCE, finally, you get HO, HOC minus 1 plus HFE, GP dash C means RB dash C, you have calculated earlier, this one here, arrow GB dash C. I mean, uh, here, inverse of this one. Okay, this parameter is calculated here. This one, inverse this, you will get RB dash C. So that you substitute here, you will get GC. So all parameters we have calculated. You can leave it here or further simplify, making some reasonable assumptions. You can arrive at smaller, simpler formula, but bigger formula, full formula. GM, we have taken the formula, like, this is by definition to IC by dou B at BC constant. This is this slide and next slide gives fundamental derivation for GM. Finally, we get that only. What we have shown GM earlier is mod IC by VT. That this derivation is done. The related equations are written, and finally, it is that only. All these views, finally, GM is that, say, GM is equal to IC minus IC naught. IC naught is less one component IC. So GM is equal to IC by VT. That is 26 milliamperes. Okay, that's what IC 20 by 26 value. IC are to mention in milliamperes. So this is what the hybrid model, low frequency model, where your objective is to find out these parameters which are BB dash, RB dash E, RB dash C, GM, then RC, are inverse of these resistance parameters. Okay, that I mean linking with H parameters which you know already. So you can draw this model and you can work out something. So what is important is remembering the formula for these parameters in the gate. There is a couple of problems, we solve them, and perhaps we'll close for today. This will take about 10 to 15 minutes. I have that much time. Um, A good transconductor amplifier should have transconductance output current by the voltage. I mean that is the transconductance. That type of you will see this type of amplifiers when we go to feedback amplifiers. We have all types of amplifiers there based on the input circuit configuration, output circuit configuration, what fashion feedback is given. So for transconductors amplifier, it should have high input impedance, high output. So high input and output resistance. That is the answer. Uh, then you have a formula, a bipolar transistor is operating in the region with the collector current of 1 milliamps. Assume that the beta of the transistor is 100. Thermal voltage VT is 25 millivolts. The transconduction GM, the input resistance R pi. The formula you have to remember for GM and R pi. Transistor in the common emitter configuration R. Says IC is given 1 milliampere here. Beta is 100, VT is 25 millivolts. GM formula is IC by VT. IC is 1 milliamperes, VT is by 25 millivolts. Then that becomes 40 milliamperes by per volt, your transconductance. Okay. Then is asked what is other parameter R pi. The relation between the R pi and other given parameter is the beta is equal to GM R pi. Then R pi is beta by GM. This formula we have seen. Then beta it is given 100 and GM we have calculated. Substitute those values. You will get R pi as 2.5 kilo. Like this, the questions will be asked in the gate, so you need to remember this formula. Then you have one more question: a BJT is biased in forward active mode, means in active region. Assume VB is 0.7 volts, KT by Q, that is VT, 25 milliamp volts, and reverse saturation current is 10 power minus 3. Okay, so here's the transconductance of the BJT is asked. Okay. VB is given, VT is given, IS is given. Correct current is saturation current times this is the diode current formula. Take eta is equal to 1. Then IC we arrive at with the given parameters of 144.6 milliamperes. Then what is asked is GM transconductance IC by VT. IC we have calculated, VT is given. So 5784 milliamperes per volt in transconductance. So 5784, 5784. This is the answer. This is again a question on the transconductance amplifier. Your input output impedances will be theoretically, practically high. Then here a low frequency pi model is given. The current IB through base of a silicon NPN transistor is 1 plus 0.1 cos 1000 pi t at 300K temperature. The R pi in the small signal model of the transistor is what is the R pi? This is IB. What is given? IB is this is given already 1 plus. R pi is the formula beta times RE. Then RE is VT by IE. Then equal to VT by IE. You can write beta times IB. So beta goes cancel VT by IB. Then VT is given 25 millivolts. At 300 degrees it will be, there is nothing but 25 degrees. So your IB is 1 milliamperes. Okay, then R pi is R pi is VT by IB. You substitute these values, then you will get 25 degrees. This IB 1 milliamperes is given here. It is AC part, it is DC part. Okay, when you calculate the DC current for this, you will get this one. This will have average value 0. The current gain of a BJT is amplifier. I mean, beta is asking beta IB. This is R pi. GM is equal to IC by BT. That is IC average. I can write beta times IB. Okay. BT IC BT IB by IB times RM. IB goes cancel. Then it becomes GM becomes beta by R pi. So beta is equal to GM R pi. This is the formula is asking, but we are always remember beta is equal to GM R pi. Beta is equal to GM R pi. This is the formula it is asking. So here I close for the day. Tomorrow we'll take up the remaining part of VGT amplifiers. So till here I will segregate the presentation and I will send it to the university. You can download and put it. Okay. And you can ask the questions on this forms. The university will forward me. Good evening. I'm learning out